Okay, hello everybody. Now, one of the things which I have to do at the beginning of every lecture is to write down the title of that lecture. And you remember that last time we had written the title as Solution of Regularization Equation and to talk about Green's function. Now, unfortunately, we couldn't complete that whole process, okay, because the solution as such is pretty much involved, okay, and that's the reason why it couldn't be completed in one lecture and we are spilling over to this one, okay. So, in this class actually what we will be doing is the plan that we had for the last lecture, that's to really solve the regularization equation, and we will be introducing the Green's function. In fact, we will be introducing the Green's function from the beginning of this lecture itself, okay, and later on what I want to do is to talk about the regularization network, okay, which is expressible in terms of the Green's function. So, that's going to be the title of this lecture, that we want to talk about Green's function in regularization network, okay. Okay, so let us begin with this topic. Now, before we do that, just a very quick summary as to what we have been doing so far in our discussions pertaining to the radial basis function chapter. Now, as I told at the beginning of the discussions related to this chapter, that we have been looking at it, okay, purely from the point of view of the interpolation of a function. So, what we have is that at the input we are having, input in the multidimensional space, in M0 dimensional spaces precisely, where we are having a non-linearly separable problem, which we are classifying ultimately, okay, by building up a non-linear interpolation function, okay. And in fact, in the last class we had seen that rather than treating it as an nonlinear interpolation function entirely, because if it is treated entirely as an interpolation function, that means to say that the surface, the multidimensional surface that we are trying to reconstruct, okay, has to necessarily pass through the given set of points, okay, given as the training samples. But we said that instead of making it like a rigid requirement that it has to pass through the given set of points, okay, we will be treating the problem not exactly like an interpolation, but like a regularization, in the sense that the cost function that we considered, okay, that included two terms. The first term was the standard error term, which is in the mean square error sense, okay, and there was a second term which minimized the derivatives of the function, okay, which means to say that there we had imparted a smoothness of the function that we are trying to interpolate, okay. So, these two things, that is to say the standard error term and the regularization term, okay, related to each other by the relative proportions decided by the factor lambda, which being the regularization parameter. So, we had these two terms combinedly leading to the error functional, okay, and we had said that this error functional is to be minimized, and the approach that we had taken, the mathematical approach that we had taken, was that we took the differential, that is to say the Frecht differential we had considered, and then the Frecht differential we had expressed in the form of the inner products, and by expressing it as inner products, okay, the condition that we had ultimately derived is that in order that that differential works out to be 0, the essential condition that we had got was in the form of Euler-Lagrange equation, which I had presented in the last class. In fact, our last class, if you remember, ended there only. So, we had an equation which we were calling as the Euler-Lagrange equation, okay, which is of this form. that it was d tilde, okay, everything, I mean d is of course in the matrix notation, d is the derivative operator and d tilde is the adjoint derivative operator of that, and then if lambda, okay, is the optimal function that we had found for f. So optimal function is written in form of f lambda of x. So the so f lambda x, although we are not writing the exact expression for f lambda s, but we are writing the expression in terms of d tilde d, okay, which means to say that it's expressible in the form of the partial differential equations involving f lambda, and this was equal to 1 upon lambda I is equal to 1 to n, okay, di minus f xi, okay, and this multiplied by the delta function that we had got, delta x minus xi vector, okay. So this is what we had got, okay, for the I mean this one is not exactly the solution, because in order to get the actual solution, what we have to do is to get some equation in the form of f lambda of x. But what we had got is I mean f lambda operated with this d tilde d operator. So it's not exactly what we are looking for, but definitely in a better form than what it was initially. So if out of this equation it is possible for us to make a solution of f lambda, then we have got what we are wanting to do, okay. So in order to solve this problem, okay, in order to solve this partial differential equation, okay, which is not very straightforward, okay, what we have to do is to solve it by making use of a class of functions which are known as Green's function, okay, and Green's functions are in fact defined always with respect to some differential operator. Now before we actually define what Green's function is, okay, look at again this expression. You see that this f lambda is operated upon with d tilde d, and both d tilde as well as d happen to be linear operators, okay. So the combined operator, if we treat d tilde d as a combined differential operator, then this combined differential operator is of course a linear differential operator that we are talking of. So this d tilde, so this is a linear differential equation that we had got, okay. So we have to now make a solution of this, and to solve this we introduce a class of function called as the Green's function, and let us see that what Green's function definition has to tell for us, okay. Now Green's function says that, I mean a function, I mean if we take a function g, okay, written as, I mean its arguments are gx comma zeta, okay, both are vector arguments. In fact in this I mean both these arguments are having the same quantity. I mean this x will be treated as the input, as you can well understand, okay, and zeta is also to be treated as an input, okay. So actually quantity wise both are inputs, but in functional definition we will be treating x as a parameter and zeta as an argument. So x will be treated as a parameter and zeta vector will be treated as an argument, but essentially they are the same quantity. Now this g of x zeta, this is called the Green's function, called the Green's function for the differential operator. Now Green's function, mind you, is always is defined with respect to some differential operator. So we can call this to be a Green's function for the differential operator L, okay. So we consider a differential operator, a linear differential operator, okay, and we are designating that linear differential operator by L, okay. So G is Green's function for differential operator L if it satisfies three conditions, okay. So the three conditions that we are putting forward is that, number one, that for a fixed zeta, because zeta happens to be the argument, in fact, you will later on find that the Green's function that we develop, okay, the Green's function will be centered around this zeta. Okay, it will be a function of x, but it will be centered around zeta. Okay, something very similar to what we had already considered for the radial basis functions. You remember that radial basis function also, what we had considered was that radial basis function was a function of the x vector, which is the input vector, but the radial basis functions also had some definite centers, and we had considered the centers of the radial basis function to be the individual patterns. Okay, so you remember that we had considered the radial basis functions centered around x0, centered around x1, like that, centered around xn. Okay, so very similarly, we take a function g of x, which is centered around zeta. Okay, so the first condition is that for a fixed zeta, okay, g of x comma zeta, okay, that's our Green's function that we are considering, is a function of x. Okay, definitely it has to be a function of x vector, and it has to satisfy the prescribed boundary condition of what is specified. Okay, so and it has to satisfy, and it satisfies the prescribed boundary conditions. Okay, so this is the number one condition for g of x to qualify as a Green's function. Okay, and the point number two is about its continuity. Okay, it says that except at the point x equal to zeta, except at the point x is equal to zeta, okay, where, I mean, x is equal to zeta means that where this variable that you are considering, okay, is at the center of the function. Okay, that means to say that at the when the parameter equals to the argument, so then there the derivatives, I mean, except at that point, everywhere else the derivatives of g of x comma zeta, okay, with respect to x are all continuous. Okay, the number of derivatives, okay, that we have to consider, because we are saying that the derivatives of g x zeta, so that means to say how many derivatives, that will be decided by this operator L, because I only say that it is a differential operator. I haven't said that differential operator of what order. Okay, I mean, it can be order 2, it can be order 3, it can be order n. So the number of derivatives, okay, which has to fulfill this condition, the conditions of continuity, the number of derivatives is determined by the order of this operator L, is determined by the order of L. Okay, so this is condition number 2. So condition number 1 is about it as a function and satisfying the boundary condition. Condition number 2 is the continuity condition, that except at the point x is equal to zeta, this function g of x zeta has to be continuous. All right, and there is a point number 3, okay, which says that with g of x zeta, okay, considered as a function of x, okay, it has to satisfy, it satisfies the partial differential equations. I am writing that as PDE. So it satisfies the partial differential equation of L g argument x zeta is equal to 0. Okay, so the differential equation that we are getting, the partial differential equation that we are getting by applying the operator L on this g function, okay, that is equal to 0 everywhere except at x is equal to zeta, except at x equal to zeta. So, except at the center point, okay, the partial differential equation that we get out of this g is equal to 0. Okay. Now, that means to say that there are two things, okay, involved about the derivative constraints and the partial differential equation. Number one is that its individual derivatives must be continuous. Number two, that when you are considering all the derivatives together expressible in the partial differential equation, that partial differential equation involving involving g should be equatable to 0. Okay. So, if these three conditions are satisfied, that means to say that gx zeta being a function of x satisfying boundary condition, number two, the continuity of g of x and the continuity of its derivatives, and number three, that its partial differential equation is equated to 0. If all these three functions, if all these three conditions are satisfied, then only we can say that g of x zeta is the Green's function for the differential operator L. And this is a very important definition that we have to keep in mind, because the solution that we will be now attempting for the Euler-Lagrange equation, okay, will be based upon the Green's function. Okay. Now, one thing, okay, I mean there is a different way of writing this, because here I wrote a statement that g x zeta operated on this L, okay, is equal to 0 except at this. Now, in mathematical language, I should be writing it more precisely as L g x zeta, okay, to be equal to delta of x minus zeta. Okay, this means one and the same thing, because when x is equal to zeta, okay, then this delta is giving us a value other than 0, and when this is not equal to, when x is not equal to zeta, okay, then delta gives us the value of 0. So, these are the three things, and now based on this Green's function definition, okay, we attempt the solution of the Euler-Lagrange equation. Euler-Lagrange equation is, as I have already told you, has been derived out of the original Tikhonov functional, which involved both the standard error term and the regularization term. Right. Now, let us consider, okay, a function, okay, which we call it as phi of x. Okay, we consider a function phi of x, okay, which is a continuous or piecewise continuous function of x. Okay, continuous or piecewise continuous function of x vector. Okay, and x vector, as I have told again and again, will be belonging to the M0 dimensional real space. So, it lies in Rm0. Okay. So, we define a function phi of x as follows, defined just now. Okay. Then the function, if we consider a function of this nature, okay, that is to say what? We consider a Green's function g of x zeta, okay, which is a Green's function with respect to, let us say, an operator L. Mind you, Green's function, every time we have to define a Green's function, we have to say its Green's function with respect to what operator. So, it is a Green's function with respect to operator L, and then we take an integral of this, that is, we multiply this Green's function with phi of zeta, okay, d of zeta, and then we integrate this over the Rm0 space. Okay. And if we do that, then f x vector, okay, we get a function involving x, right, because here we are integrating it in the zeta space, but ultimately this integral quantity as a whole okay, becomes a function of x. So we are calling that as a function of x. So if we write a function of x like this, function of x in the form of, in the form of this integral, okay, where g is a Green's function, in that case this fx is equal to this, okay. This is a solution of the differential equation. This is a solution, yes? L fx is equal to phi x, okay, not LGX. In fact, it originates from LGX. You are not 100% wrong, okay, because what you can do is that, I can understand that what thinking he had in mind, that if we now operate both these sides with the operator L, okay, then what you are getting is that on the left hand side you are getting L fx, okay, and on the right hand side you are getting L operated on with this entire integral expression. Of course, that means to say that the L operator could be taken inside the integral sign also. So it could be treated as an integral over Rm0 space Lgx zeta. And Lgx zeta we very much know, okay, just now we got Lx zeta. Lx zeta means what? It is delta of x minus zeta, okay. In fact, if it is a delta function multiplied by phi function, okay, then delta has got a value that except at the point of x equal to zeta, okay, everywhere else the delta function is having a value equal to 0. So ultimately we get what? Very good, very good. Ultimately we get phi of x. So ultimately what you are getting is that this is a solution of L fx, okay, is equal to phi x. So the very fact that L fx is equal to phi x has been already worked out by some of the students here, but just for the benefit of those who couldn't follow this done very hurriedly, because we didn't write down the every steps, okay, but for the benefit of those who are little slow in understanding this aspect of the equation, okay, so for the benefit of them, what I say is that by applying, well, let's call this one as equation number 1, okay. So I can say that applying the operator L, okay, applying the operator L, the differential operator in fact, to 1. When I say applying the operator L to 1, that means to say that it will be operated on both the sides, left hand side as well as the right hand side. So by applying that, what we get is that L fx, okay, L fx is equal to L integral Rm0, okay, g x zeta, okay, phi zeta, okay, d zeta, and this, as I told you just now, can be written as Rm L g x zeta x comma zeta phi zeta d zeta, and this being equal to the delta function, it is R integral over Rm0 delta x minus zeta phi zeta, okay, d zeta, and this is simply equal to phi x from the very definition of the delta function. Is it very clear? So we have got this. So that means to say what? That if we have got a Green's function g, okay, then g is actually a Green's function with respect to the derivative, and then if this is expressible as an integral equation like this, then effectively the solution of this becomes L fx is equal to phi x. Okay, so this is a very important relation that we will be making use of, that here we are getting L fx is equal to phi x. Okay. Now ultimately what we are trying to do, we are trying to solve the Euler-Lagrange equation. Okay. Now Euler-Lagrange equation says d tilde d f lambda is equal to this quantity. Okay. Now d tilde d itself combinedly is a linear differential operator. So I can call this d tilde d together to be the operator L. So in that case it becomes L f lambda is equal to this. So in order to solve Euler-Lagrange equation, simply what we will be doing is to define my L operator as d tilde d. Okay. So, we define the operator L like this, and then we consider phi of zeta to be the term that we had got in the Euler-Lagrange equation. So, here you see that, I mean, ultimately I am going to express the Euler-Lagrange equation in exactly this form. Okay, if I call this to be equation number 2, then I want to represent Euler-Lagrange equation in the form given by 2. So, 2 means that L operated on, I mean F operated with L, and L we are taking to be the d tilde d. Okay. So, left hand side is obtained, and right hand side, this whole thing phi of x we are treating like this. So, here what we are doing is that we are defining phi zeta then to be equal to 1 by lambda summation I equal to 1 to n, okay, di minus f x I, okay, delta zeta minus xi. Okay. Refer to Euler-Lagrange equation once again. I mean, here what we have simply done is that instead of x we had put zeta. Okay, does not matter. Okay, so we are calling this whole function to be, I mean, here it becomes phi of x, and by defining it like this it becomes phi of zeta. So, phi of zeta is defined in this format. Okay. If that is so, okay, that means to say that L f lambda is equal to this. In that case, in what form can we express f of lambda? Very correct. Because you see L f lambda is equal to phi zeta, and since it is this, okay, then f lambda is expressible as, I mean f lambda of x, of course. So, f lambda of x is going to be the integral equation, integral involving what? Green's function, and then the phi function. So, it will be Green's function, that is g of x zeta, okay, and then the phi term, and the phi is phi zeta, because the argument, I mean the variable that we are considering under the integral sign is the variable is zeta. Okay. So, we will be writing this phi zeta, okay, d zeta, okay, and this will be integrated in the Rm0 space. So, now looks like that our solution is getting closer, right. So, the solution of f lambda, that is what we have been looking for, is equal to this, and this can be written simply as integral Rm0, okay, just I substitute the expression for phi zeta, x zeta, okay, and here I am going to write 1 by lambda, that is whole substitution of this, summation I is equal to 1 to n di minus fxi, okay, delta zeta minus xi, okay, and then d zeta is there. Okay. Now, here actually first comes integral and then comes summation. Okay. The order of integration and summation can be interchanged in this case. Okay. So, if we interchange the order of summation and integration, so by interchanging the order of summation and integral in integration, what we get is, I will show in the next page, that is to say f lambda of x is equal to 1 by lambda summation I is equal to 1 to n di minus fxi. Okay, if this comes out, this comes out, this summation I am taking out, okay, and then what remains as the integral is gx zeta delta zeta minus xi d zeta. That is correct. So, then we had the leftover as the integral Rm0 g x zeta delta x minus zeta d zeta. Correct, correct, correct. You are very correct, because here we are, yes, 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 yes. This is zeta minus x, zeta minus xi. Very, very correct. Yes, yes, that's what it is. Right. Thank you very much. So now this one, okay, this one is what? This one is, this term remains as it is, that is summation 1 by lambda summation I is equal to 1 to n di minus fxi, and then what will be this? Correct, g of x comma xi. Okay, this is a very interesting expression. Okay, so that means to say that the minimizing solution, now what is after all f lambda x? F lambda x is the minimizing solution, okay, to this interpolation problem, okay, to this, not interpolation, strictly speaking, regularization problem. Okay. Now, this is actually obtained as a solution of, this is actually obtained as a superposition of n different Green's function. And what is n? N is the number of training patterns that we are feeding. Okay. So, corresponding to the number of training patterns n, we have to constitute n number of different Green's function. Okay. So, it is a linear superposition. So, the solution is obtained as a linear superposition of n number of Green's function. So, I can say that the minimizing solution, which is f lambda x, okay, is a linear superposition of n Green's function. And what are these Green's functions? You can see that how are we getting n different Green's function? Quite simple, because we have got gx comma xi, and what is xi? Xi is the center of that function, and we have got I varying from 1 to n. So, that means to say that we have got gx comma x1, x comma x2, x comma x3, like that up to x comma xn, and we have got n such different Green's function possible. Okay. So, for every input x, so x is our input, okay, and we already have got the Green's function which are centered around the n number of training inputs which we already got. Okay. So, x will be mapped into gxxi, okay, and there are n such mappings which will be possible, and all these n Green's functionally mapped outputs, okay, have to be linearly combined. So, you see that effectively what is this g functions acting for? This g function is acting as a basis, okay. And what is this di minus fxi? This di minus xi is represented in the form of coefficients of expansion. You see that if we treat g of, I mean in this summation equation, this is a summation equation, right? In this summation equation, there are n such Green's functions. So, if we treat all these n different Green's functions, okay, to be the basis, okay, then the coefficients which are associated with this becomes the coefficients of expansion. Means as if to say that treating these as basis functions, we are realizing the ultimate function f lambda as a summation of basis functions, just like the way we express any function as a summation of basis functions, taking the complex exponential to be the basis functions, as we do in the case of the Fourier transforms, taking the cosines to be the basis functions in the case of discrete, I mean cosine transforms, like that. So, this will form the basis function. So, Green's function acting as the basis, and this term, that is di minus fxi, okay, not exactly di minus fxi, I should say 1 by lambda di minus fxi, they represent the coefficients of expansion. And Green's function acts as basis function. Now, we have to determine all these expansion coefficients. Okay, means as if to say that we can also say that if this whole thing 1 by lambda di minus fxi, the coefficients of expansion that we have got, if this whole thing 1 by lambda di minus fxi we call as wi, in that case wi is the coefficient of expansion. So then if lambda x is manageable in a form of summation of wi times g of x xi. Okay. So if we treat it that way, so if we let that wi is equal to 1 by lambda di minus fxi, okay, which we have to define for I is equal to 1 to up to n. So this should be the equation number 3 for us. Okay. So here there are n such w's which one can define. Okay. Then we may recast the minimization solution. Okay. Then the minimization solution can be rewritten as what? If lambda x equal to summation wi g x comma xi, sorry, x comma xi, and this has to be summed up for I is equal to 1 to n. Okay. Now this is a general term. I mean, x is the input, x is any input. So you take x as any input, and then you have to operate this through this Green's function gx comma xi's. There are n such xi's which are available, n such centers which are available. So as an input to it, as the input to this, we can feed any of these xi's, isn't it? We can feed x1 as input, we can feed x2 as input, we can feed up to xn as input. That means to say that this function, this minimized solution, we can evaluate at all these n different points. So the above may be evaluated at x of j, we can say, because we are using this as the index I, we can say this may be evaluated as at x of j, where j is equal to 1 to up to n. So if we do that, then we can write if lambda of x j vector is equal to summation I is equal to 1 to n wi g of xj, yes, xj comma xi. Okay. And this we can compute for j is equal to 1 to up to n. So this and this are basically the same, only thing is that this is a general solution and these are all these n different, I mean the general solution evaluated at n different points. Okay. Call it as equation number 4. Okay. So now what we can do is that this equation number 3 and the equation number 4, which can actually be computed for n different points. Equation number 3 also can be computed for n different points. Equation number 4 also can be computed for n different points with j is equal to 1 to n. So then we can represent the whole equation, okay, the entire minimization equation that we have got. Okay, instead of writing it in this form, we can express in the matrix form if we define, okay, the matrices like this. So we make some definitions. We introduce some definitions where all this f lambda x1, okay, I mean f lambda x1 means that it is the f lambda evaluated at the point x1, okay. Like that one can evaluate f lambda at the point x2 and up to f lambda can be evaluated at xn, okay. This, if we treat as a vector, column vector, then we can call this combinedly by f lambda vector. So, the definition of f lambda vector is that it consists of n different elements, whose elements are the functions evaluated at n such different points, okay. And likewise, we have got the desired outputs, okay. For the pattern x1, the desired output is d1. For the pattern x2, the desired output is d2. For the pattern xn, the desired output is dn. So, now I can write everything together in the form of a vector, okay, and call this as the d vector, okay. And now you see that I have got this g functions, this Green's function, and here it becomes g of xj comma xi, okay. So, which means to say that I can treat any of these, I mean I can have n different centers to that Green point, I mean to this Green's function, and this can be evaluated again at n different points. So, for every center it can be evaluated for n different points. Every center it can be evaluated for n different points, meaning that for n centers it can be evaluated at n by n number of points. So, in effect, out of this g xj comma xi, we are going to get a matrix of size n by n, okay. So, we are going to define that matrix, okay, which I mean translated in raw terms would mean that we got a function g of x1 comma x1, which means to say evaluated at x1, centered around x1. Then we can take g of x1 comma x2, the Green's function centered at x2, evaluated at x1, and likewise Green's function, okay, having center at xn but evaluated at x1, okay. And then again we can say Green's function, okay, whose center is at x2, whose center is at x1, but which is evaluated at x2. In the first row you see that everything is evaluated at the point x1. In the second row everything is evaluated at the point x2. So, evaluated at x2 with center x2, here evaluated at x2 with center as xn, okay. And here it is g evaluated at xn with center at x1, evaluated at xn, center as x2. So, this column effectively corresponds to the center. So, this is the center 1, this is the center 2, last one is the center n, and the row corresponds to at what point is it evaluated. So, it is the first point of evaluation, that is x1, this is second point of evaluation, this one is nth point of evaluation. So, this is g xn comma xn, okay. So, in effect we are getting an n by n matrix, and this matrix combinedly we are calling as the G matrix, right. And what else is to be defined? Yes, this Wi's. You see, Wi also we can define at n different points, okay. So, I can compute W1, W2, W3 up to Wn. So, combinedly we should write another vector, okay, which because I may not be having place in the bottom. So, I am writing on top. So, this one is W1, W2 up to Wn, okay. All these different W's are possible, n different such W's are possible, and combinedly we are going to call it as the W vector, right. So, now I think this definition is nothing but just putting all this n together in one representation, okay. Earlier we had n different representations of this equation, n different instances of this equation with I is equal to 1 to etc. up to n. And now this same equation, that is equation number 3, what we can write down in the combined form? W vector, I mean equation number 3 I am saying, equation number 3 becomes W vector is equal to 1 by lambda d vector minus f lambda vector. Okay. So, that is the matrix form of representation of equation number 3. And likewise, the matrix form of equation number 4 will be f lambda vector, or f lambda matrix rather, will be equal to GW, G matrix multiplied by W vector. Okay. So, the two equations, so equations 3 and equations 4 in the vector matrix form, I mean this is represented in the scalar form, individual scalar form. So, in the vector matrix notation, equation number 3 and 4 may be rewritten as. So, in matrix vector form, okay, equation 3 and equation 4, okay, they are not new. I mean, it's just another way of representing in the matrix vector form. So, this may be rewritten as W vector is equal to 1 by lambda d vector minus f lambda vector. Yeah, f lambda is the minimum one, but minimum one is the one that we are seeking. Okay, my dear. Yeah, you are correct. See, that means to say that you see that when we get okay, I mean when we obtain the final solution, the final solution to it, when we got the final wi's that we are going to get, okay, is di minus f lambda of xi. Okay. F lambda is w times g, yes.
And w itself involves f lambda.
Oh, that's okay. I mean, let me clear your the confusion. You see what you are trying to tell me. See, what we have got for the f lambda is this equation, right? Fxi we got, and the minimized solution we are getting as f lambda x. All right, I accept. So that means to say that given the function fxi, okay, we have got f lambda x. Now what we have been doing is that if ultimately we get the solution as f lambda, when we got the ultimate solution, minimized solution f lambda, and at that point if we want to calculate that what is the coefficient, okay, when we have obtained the solution, that means to say that if we are solving for w, okay, if we are obtaining the solution for w under the minimized functional case, in that case I should not be taking that as f anymore, I should replace f by f lambda, because already we will be getting f lambda to be the solution of that. Followed? Okay. So this becomes the minimized solution case. So what I have to do is that this one is f lambda, which I can call as the equation number 5, and this f lambda should be equal to GW, okay, which you have said. Okay, only thing is that I mean you had some confusion about putting f lambda over here. Now f lambda we can only put, okay, when this is the final solution of w, okay, because ultimately that's the w that we are going to solve at the end. Okay. So now if from equation number 5 and 6 we eliminate f lambda, so by eliminating f lambda, okay, between 5 and 6, what do we get? We get here, because it is GW here, okay, we can have this to be lambda times W, okay, lambda times W to be equal to d minus f lambda, but that makes it okay, I mean that that's one and the same as writing that I can write it as G plus lambda. I mean, if I treat I to be an identity matrix, okay, so I can write it as G plus lambda I W to be equal to D, okay, where I is the n by n identity matrix. All right. So then this is what we get, and we call G matrix as, G is referred to as Green's matrix because it's a matrix realized out of Green's function. Right. So if we have this, now can you see one thing? I mean, this is equation, this is an equation that we have got, and that is equation number 7. Okay. Doesn't it remind us of the equation which we had got while solving the interpolation equation involving the radial basis function? What was the interpolation equation? Remember, that was phi W. Okay, phi matrix W is equal to D. And here we are getting G plus lambda I times W equal to D. As if to say that whatever role, okay, the phi functions, the radial basis functions had played, okay, for interpolation, the similar type of action is being taken by the G function to solve the regularization. So what was phi for interpolation becomes G plus lambda I, okay, for the regularization. Now for regularization you again see that it is not G alone, okay, it is G plus a term lambda I, okay, where there is a definite involvement with this term. Okay, I mean, why did we introduce this I? Because we could have satisfied the equation without introducing this I also, but just to write it in a consistent form, that if we write these things in the parenthesis form, then there has to be this lambda. Lambda is a scalar quantity, okay, the lambda has to be multiplied by a matrix, so that together this G plus lambda I becomes a matrix. Because what we now have to do is that if we now want to solve for this W, okay, what we indeed be doing is to take the inverse of G plus lambda I. So whatever arguments we had put forward, okay, about the existence of inverse functions for the case of phi will now come into being for the G functions as well. Okay. That means to say that there should be only a certain class of functions, okay, which for which this G plus lambda I, this matrix will be positive definite. Okay. And only if it is positive definite, then G plus lambda I inverse, okay, should exist, okay, and then we can solve for W. And what are the G functions, okay, that fulfill this criteria? In fact, it's called as Mitchell's criteria. Okay, the Mitchell's criteria, we saw that the positive definite criteria is fulfilled by certain class of functions for phi. What were they? We took as examples the Gaussian functions. The Gaussian functions could do, and then the multiquadrics and the inverse multiquadrics. These three functions could fulfill that condition. Okay. Now here for the case of G plus lambda I, okay, we find that the Gaussian as well as the multiquadrics, okay, which are essentially local functions, okay, they become positive definite and they can be used as Green's function. Okay. And another point which should be noted for the Green's function is that we have defined the differential operator. How we defined differential operator L? in this definition it is L is equal to d tilde d, and what is d tilde? D tilde is nothing but the adjoint of this d. Okay. So now since it is defined as d tilde d, I mean you will find that the adjoint of L, I mean now if we take the adjoint of L, okay, we will find that the adjoint of L becomes equal to the operator L itself. That means to say that the operator L, I mean it can be proved that since it is defined as d tilde d, the adjoint of L, if you take, the adjoint becomes the same operator L, okay, which means to say that L is self-adjoint, and if L is self-adjoint, then G matrix becomes a symmetric matrix. That means to say that G xi xj, whatever we have as G xi xj becomes equal to G xj xi. Okay. Now I could discuss further. In fact, the title of the talk said that it is, I mean using Green's function we want to realize a regularization network. Now this is the equation, okay, which will form the basis for explaining the regularization network. Okay, now that we have got this equation, equation number 4, okay, or better in the matrix form as equation number 6, it is easy for us to construct the regularization network, which I will show. Till then, bye.